Let's start with an example here that recalls how we work with unit conversions. So we have here a student averaged 45 miles per hour on a trip. What was the student's speed in terms of feet per second? Well, the important things to remember here is that when we are working with units of any kind, units are a multiplication statement. So 45 miles per hour literally means 45 times of miles in 1 hour. So I like to write that as 45 miles over 1 hour. And the 45 miles, recall, is just simply us saying here's a mile, there's another mile, and another mile we've traveled, and there's going to be 45 of those that we have. So we have 45 times of these miles that are happening in 1 hour. So I like to write that using some symbolic math as saying 45 miles. There's a little hidden multiplication symbol between the 45 and the miles. So that's 45 times of miles over 1 hour. Over 1 hour. Now this is a truth. This is a truth of the phrase. We can't change this meaning without changing the truth that it holds. So all we want to do here is not change this, but we want to change its appearance. So what we can do anytime in math, if we have a number, is we can always multiply by 1, and multiplying by 1 does not change something's meaning, it just changes its appearance. So I'm going to multiply by 1 here, but we're going to do so in a hidden way. Instead of writing 45 miles per hour times 1, I'm going to make that 1 look a little different. So for the number 1, remember that a number 1 can be represented as a fraction, maybe something like 1 over 1, where I'm dividing something by itself, so long as that something is not causing a divide by 0 error. So I've got 1 divided by 1 is just as truthful as 1. And as I stated, this comes from the logic of having something divided by itself, something that is divided by something equal to it. Well, we can use the fact that math is just a model of logic to expand this ability to not just mean it has to look the same on the top and bottom, but instead it just has to mean the same on the top and bottom. So what I'm thinking we could do here is we could do a conversion with some of the units we have. Like, for example, I recognize that 5,280 feet is the same thing as 1 mile. So I'm going to make my number 1 be 5,280 feet over 1 mile. Now this is a fraction that means 1. It's the same thing over itself. So this I can multiply in without changing anything. So I can say I'm going to multiply in by 5,280 feet over 1 mile. And as we know from working with fractions, we can predict that we are going to be able to cancel the miles here with the miles there, because there's nothing but hidden multiplication symbols between all of these things. And since one instance of the miles appears on the numerator and the other appears on the denominator, they're going to cancel away. It's going to be something divided by itself that I can ignore as if it's a number 1. So we've been able to change our units into now feet per hour, which is closer to what we'd like because we would like feet per second. So the other things that we can multiply by, the other hidden number 1s, will allow us to change the hours now into seconds. Well, let's take a look at some of these. I've got 60 minutes in 1 hour, so I could write that 60 minutes over 1 hour is a number 1. It's a hidden number 1 because it's something divided by itself. Well, 60 minutes over 1 hour, if I multiply that in right here, is going to have a little bit of difficulty. Let's try it and see what happens. 60 minutes over 1 hour. If we multiply this through, notice that the hours will not be able to cancel with these hours. There is not one instance on the numerator and one instance on the denominator. But that's okay. What we can do is, instead of putting this fraction in exactly, we will just simply recognize that we could have rewritten this as 1 hour over 60 minutes. Remember, that's still the same thing as something divided by itself. And if I put that in instead, now I've got an orientation, an organization that will allow me to cancel those hours away. So I have 60 minutes on the denominator and 1 hour on the numerator. Now I can predict that those hours will cancel away. And that will leave me with, it looks like the units of feet, which I want, and minutes, which is not exactly what I want, but I can use it to get to seconds. So we have another relationship here, which I can put into my equation by recognizing that I need to put the minutes on the numerator so that they cancel away. And I need to put the equivalent of 1 minute on the denominator, which I'm going to write as 60 seconds. So notice that now I have the ability to cancel the minutes and the minutes. I have done nothing in this entire problem except for multiply by 1. So I get to put equal signs that say that the thing at the very beginning, the 45 miles per hour, is just the exact same thing as the units of feet per second that I'm going to be able to get. If we multiply this all the way through, 45 miles times 5,280 feet times 1 times 1, we're going to get a number that has feet for its units. On the denominator, we have 1 times 1 times 60 times 60, and that's going to get us something with the units of seconds. So we'll pull out our calculator and we'll type this away. Now when I use my calculator to do all that multiplication, I get 237,600 feet on the numerator, and on the denominator I get 3,600 seconds. Now this is true, but it's not exactly what we're looking at as per 1 second. Remember that this is like per 1 second. So how do I make this something easier? Well, again, we can use our calculator and just perform this division. So I'm going to do 237,600 divided by 3,600, and I'm going to see exactly what I get. Now in doing so, I got 6.6 feet per second. And we'll want to include those units because we really want to talk about what we are currently viewing this scenario as. So there you have it, 6.6 feet per second is the exact same thing as doing 45 miles per hour. And I want to think that that looks decently reasonable. I mean, 6 feet per second, I'm about 6 feet tall, so if something's traveling my height every second, then it's going to be moving at a decent speed, and probably needing to be something that's equivalent to what a car could put out. 45 miles per hour is a reasonable attachment to that in my mind, so I'm going to say that this is a good answer, and that we'll box it and call it. Now that we've been able to review how we can convert from one unit to another, it's important that we take a look at how that becomes a little tricky when we're dealing with dimensions like area and volume. So I've got an example here. A room is 10 feet by 12 feet. Now I am a visual person, so I'm going to draw that immediately because I would like to keep as much out of my head as possible so that I can focus on the next steps, not the last information. So if I put 10 feet here, and I'm not worrying about drawing this too much to scale. You know, channel my inner Bob Ross here and just kind of make a happy little picture. So I have 10 feet by 12 feet. If I wanted to sketch that out for what it means, 10 feet means that I have gone along this for 10 increments. So that's 3, 4, 5, 6, 7, 8, 9, 10-ish. You get the right idea. If I took that, I could track that all the way across the room and see that that gets me 10 little sections here, all the way across the room. So that 1 foot I can track all the way across the room. For the 12 feet, I can do the exact same thing. I can say that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that'd be, I think we could track that all the way through as well. And take a look at what we've created. We've created squares that fill up the room, and each of these squares is 1 foot by 1 foot. So us being mathematicians and trying to keep our names as simple as possible, we will often refer to a size of area, a unit of area, as a square foot. And it's because we are literally putting squares that are 1 foot by 1 foot down. So this is a 1 square foot. A 1 square foot is the equivalent of 1 of those squares. And sometimes we will write this, since it's 1 foot by 1 foot, and we've already explored how units are just multiplication, another way of writing that more easily is we write that as 1 foot squared. And that's because what we have looked at here is 1 times 1 is 1, and foot times foot is 2 repetitions of foot. And something that's repeated twice, just like 9 times 9 or x times x, makes a square. So we could make that as a 1 foot square is how we would read this out loud. 1 foot to the 2nd power, because there are 2 repetitions of feet in my multiplication problem. Okay, now we're being asked about how many square yards are in the room. Well, we need a conversion for that. I remember that 1 yard is equal to 3 feet. So let's go through our picture and section this out in terms of yards. Well, 3 feet here, these 3 feet, could get grouped together as a yard. And these 3 feet going down could get grouped together as a yard. So that means that if I wanted to look at the square yard, it's all of these square feet, 9 of them in fact. Now that's interesting. So we've got 1 yard is 3 feet, but 1 square yard is 9 feet. Oh, but not 9 feet, because I didn't highlight a length, I highlighted an area. These are 9 square feet. 9 squares that were foot by foot made up 1 square that's a yard by yard. Well, I think we've found a pattern that helps us do this math. What we've done is we have literally taken these things and multiplied them. So we have the 3 feet had to get multiplied by another 3 feet to create 9 square feet, because those were the dimensions. Let's do a little model over here. So we literally took where we had 1, 2, 3 going across and 3 going down, and used all of those, that 3 by 3, to create 1 square yard. And that gives us insight into how we can do conversions when they're dealing with dimensions. We have to keep track of the fact that area is going to always be a length times a width. So if we're talking about a square area, it's always going to be a length times the same length. Okay, so I think we've got enough insight to now begin our problem. If we go through and highlight this all the way through, making these square yards nice and apparent, I think we're going to have about 3 going down with a little extra. I think I've missed 1 layer, so let's put in a little layer here to make that actually 10 going down. So I think we're going to miss a little bit on the bottom, and we're going to miss a little bit on the sides, but we should get a reasonable guess that it's going to be 4 across and 3-ish down. Okay, so that would mean a total of 12, a little more than 12 square yards should be our answer. Let's see how we can work some of the more particular details using algebra. So I'm going to restart this problem, and we're going to approach it from an algebra perspective, an equation perspective, now that we have the insight from this. So we have a room that is 12 feet by 10 feet. So I can write that off to the side real quick as saying, okay, then I've got an area. An area is going to be length times width. And in this situation, my length was 10 feet, I'll include the units. And my width was 12 feet, I'll include the units. So that if I was to count every single square, and you can do this by drawing it out, every single square, there should be 12 groups of 10 or 10 groups of 12, giving me 120 squares that are each 1 foot by 1 foot. So that's 120 square feet is the area of this room. Okay, now we've got how many square yards are in the room. Well, I'm going to start with my truth. My truth is I have 120 square feet. And I'm going to recall that 12 feet were in, no, excuse me, 3 feet. 3 feet were in 1 yard. And that when I made a square using these units, I multiplied something by itself. So that must mean that if I take the 3 feet and I multiply it by the 3 feet, it's the same thing as me taking the 1 yard and multiplying it by the 1 yard, because they're the same thing, they just look different. Well, that means that 9 square feet, which I could write like this, is the same thing as 1 square yard. Now, a way that I like to do that all at once in my work is I like to make the fraction, that hidden number 1, nice and obvious. Remember that we start with a hidden number 1, and I can say that that hidden number 1 is going to be 3 feet per 1 yard. Well, since here we recognize that multiplying something by itself is the action we need to take, and here, this something is a number 1, which I can always multiply by a number 1 without changing its meaning, I could say that this is the same thing as 3 feet over 1 yard, where I've made that into a square. Really clever algebra trick here. We can square 1, because that's nothing more than 1 times 1, which is still 1. And that gives us the truth that we were seeking out. I have 9 square feet for every 1 square yard. So if I want to take that and put that into my statement here, then I've got my 120 square feet. I have square feet in this fraction, but I'm going to make sure I flip it so that the units cancel away. So I'm going to multiply by 9 square feet per 1 square yard. I now have units that can cancel. So I will be left with 120 times 1 square yards. That's 120 square yards. And on the denominator, I have 1 times 9, which will just be 9. So I've got 120 square yards divided by 9. Let's make that look a little more simple. I can do 120 divided by 3, which would get 40. So 40 square yards divided by 3 is what happens when I divide the top and bottom both by 3. But I want to make it even simpler than that. So this is going to come out to about 13.3 repeating square yards if we did this in our calculator. So 13.3 repeating square yards is the area that we have for a room that is 10 feet by 12 feet. And this, I think, makes good sense, because we were looking at the picture from the last example, and if we remember, this was going to be 12 pink squares with a little something extra, so we got an answer of about 13 squares, and that makes sense to me, because I think I could go back here and I could find another, let's see, here's 3, there's 3, and there's 3, that I could have made into another square, leaving me with a little bit extra left over. In fact, a third of a square would have been left over. Oh, and that's exactly what we have here. We have 13 full squares and then a third of a square left over, so we're good to go.